Swayam Prabha. Digital India. Educated India.
Hello, welcome to the second week of lectures on compliant mechanisms, principles and design. This week we are going to cover two things. One is elastic pairs, as we are calling them in this course, and how to model them and how to use them. That will be the first one part of this week's lectures. This is the second week. The other part of this week's lectures are going to focus on using finite element analysis for both small displacements and large displacements to model compliant mechanisms, not just with elastic pairs, but with elastic pairs as well as elastic segments. So, there are two parts. The first part would be focusing on the first three lectures, and second part will be taken up in the next three lectures. Okay. In this lecture and the one that follows this, we are going to talk about elastic flexures and elastic pairs. So, let me first start with by showing a device that has elastic flexures. You see, we have over here and here, here, here and there. We have elastic pairs or joints which connect relatively rigid portions, meaning that if I look at this segment, right. So, it has an elastic pair here, this is rigid, and if I look at this one, so there is elastic pair here as well as down here, right. So, there are elastic pairs, meaning joints that connect. It is still a monolithic mechanism, or what we call a fully compliant mechanism, but it has these elastic flexures which give it a discrete compliance, and you can see how it works. So, this particular one, if I hold it at these 2 points and do this, it is going to go like that, right. So, that is if I put a load here, like if I put my finger, I can see the mechanical advantage, a little force. I am applying small force over here and a large force over here, right. So, this is the elastic flexure based compliant mechanism. Let us contrast that with the one that has elastic segments. Okay. So, here I apply force here, it goes like this. Okay. So, or if I flip it like this, the way I had, I apply force here, it goes. If I put my finger here, I can feel the amplified force over here. This elastic segment based one, that is not we are going to talk about today. We are going to talk about this one. Before I start, I have to say how do we compare the two, the one that has discrete compliance like this, the other one that I showed which is this, which has distributed compliance. Which is better? If you were to play with these things, you will see the difference. Let me show it to you by first taking the discrete compliant one. If I apply force, it is going like this, but what would happen is that if I do not take enough care, I can flex these elastic pairs a lot. In fact, if you were to look closely here, they already undergo some plastic deformation. In fact, the color of this polypropylene changes, becomes more whitish, indicating that it has undergone plastic deformation. Sometimes they are called plastic hinges as well, not because they are made of plastic materials, but they have undergone plastic deformation, and in fact their stiffness also changes a little bit. And if I do not take enough care, this thing can actually go out of plane. So, if when I am applying force like this, okay, it can actually go out of plane, because out of plane stiffness sometimes can be lower than in plane stiffness, but here we have made it thick enough that it is not doing, but if you do not take care, it can go. That does not happen in the distributed compliant mechanisms. Another thing is that the range of motion here will be quite limited, because if I deform it by a large motion, so that these things undergo relative rotation a lot, then these things will undergo a lot of stress and they might fail. Like I said, they already have undergone plastic deformation. but even then they are used quite a bit in various applications. So, let us look at this discrete compliance today made of elastic pairs. This we had already seen in the first lecture. You take a sheet of material and you can create something like this very easily. So, all these are elastic pairs, we have joints there, right, they are the elastic pairs. In fact, we had said that this actually comes from a 4 bar linkage. If apply force over here by turning the screw, this is going to move like this. If I move it back and forth, the screw after it touches, I can make this move. It is suitable for precision motions which are small motions, because these elastic pairs are flexures, as they are called, flexures. Okay, they are flexible joints. They are used for very small motions, so that you can get precise motion where resolution or the smallest motion that you can repeatedly apply. That is the definition of precision mechanisms, where repeatability is important. That means that there should not be any effects from the environment, noise. There could be temperature or friction, backlash, those are not there in compliance anyway, they are certainly not there in flexures. That is why people use them in precision mechanisms. And this is the plastic hinge or living hinge, as we call it. Again, plastic, not because it is made of plastic material such as this is the plastic hinge, but it has undergone plastic deformation most often. Injection molding, people do this specially to make this little bit more flexible than the rest of the material. You would see when you take plastic boxes, you would see decoloring or slight softening of the color in these portions. There are a number of these things that we see around. And it is not at all new. A person named Kevin Tofig had used this mechanism back in 1960s, where he had used that in a galvanometer adjustment mechanism. Here there is a set screw, so that means that you can apply force on this link. If I were to number the segments 1, 2, 3, 4, it is like a 4 bar linkage essentially. On the 4th segment, apply a force like this by having a screw over here. By turning a screw, you will apply a force like this. It would move ever so little what is needed in optical instruments or some of these precision instruments like galvanometer. There are mirror here, mirror has to be turned a little bit. So, this is 1960s work people have used. Focus on this geometry of the flexure. Here there is a circular segment which is very short, so we can call it elastic pair rather than calling elastic segment. This is the crucial thing for this. Okay. This can be analyzed and we can see how much it moves in what direction and whether it is affected by thermal fluctuations and so forth. That is what people worry about in these flexure based mechanisms and elastic pair mechanisms. The circular notch elastic pair is very common. So, what you need to do is, if you have a large plate, if you want to create a circular flexure there, you have something like this. You remove this material. So, let me use that by erasing. Oh, the whole thing goes if I try to erase. So, I will just redraw it then. I thought I can erase selectively, but if I have a plate, it does work in a way. I can actually do this. I can erase this line, okay, and then redraw it. So, basically I have, oh, still in the eraser mode. Yeah. So, we have this circular flexure, it is like this. Okay. So, that is what is shown over here in 3 dimensions. We are removing basically a cylinder amount of material, but in 2 halves, right. This is one part that is removed and this other part that is removed. So, if I were to fix one of these parts and apply a moment or a torque on it, then it will flex. So, this portion will elastically deform because this is narrow, right. This portion will elastically deform and that forms the elastic pair. So, we can actually think of this as there is a rigid body over there, there is another rigid body here. These two we can say are connected with effectively a pin joint. Okay, that is an elastic pair. Of course, this pin joint is not without its stiffness. So, the effect of stiffness can be modeled by putting a torsion spring. Okay, that blue one that we have put there is a torsion spring which would imitate the elastic deformation of this portion there. So, we will denote by kappa, which will have units Newton meter per radian, meaning that if you multiply this kappa with the angle of rotation of this, because this is going to deform in some manner, right. So, something like this it will deform. Okay. It will not extend like I have drawn, but it will bend, right. So, that bending is denoted with a pin joint here with a torsion spring kappa there, that will give you the same resistance that this circular notch elastic pair would give, and it has been used extensively in precision machines. Here is one of those, what is called a parallel motion flexure mechanism, and you would notice these circular notch elastic pairs or circular notch hinges. Sometimes people call it also a flexure. Okay. What does this do? This is, it is actually called a base. So, this is like a fixed frame, okay. And there are these things, it is like a parallelogram or a rectangle 4 bar mechanism. This is the one that is, we can call it a stage, and this stage here, when you apply force anywhere, you can apply force on this body or this body or this body. Wherever you apply, this stage is not going to rotate, it is going to basically translate in two directions. It will definitely move, because if I were to draw the equivalent of that here, each flexural joint. So, the base is here, okay, this is the base that is fixed, and then here we have the moving stage, okay, moving stage. And because we have these elastic pairs, we must show the torsion springs here. There is torsion spring, torsion spring, torsion spring, torsion spring. When we model this, we assume that these things are actually rigid, right. So, these things are not flexible. You see, this portion and this portion are relatively rigid compared to the flexure joints. Okay. Now, if there were to be a force applied anywhere for this mechanism, it can be like this, whichever way you do, because of its geometry, which is like a rectangle, like a parallelogram, it is going to only move in that direction and in that direction. Okay. In fact, if you move it in this direction, it is actually going to come down, because it is going to go like that, right. This joint is going to come there, this joint is going to come there, it is going to move horizontally. That is why it is called parallel motion. The motion of the stage is going to be parallel to the base, okay. And that is what people want. You do not want unnecessary rotations of the stage, and one can improve this further. Now, what you see here, earlier one we had this much, the 4 joints. So, this was the stage. Now, it has been moved by putting 4 more. Let me show them in different colors. We have 4 more flexures here. So, it is folded back. So, this was the stage that was capable of moving like this and like this in 2 dimensions, but no rotation because of the constraints that are put in with elastic pairs. Now, another one is added on top of that. So, this one will still have this motion and this motion, but what you can do by putting it down, this component, that is a vertical, or this component that moves in this direction can be compensated over here. So, this stage now does not move much in this. I will not say it will not move at all, but compared to the previous stage that we have here, the motion in this direction will be reduced over here by having this compensatory one. You might actually think that instead of this portion, let me encircle what I mean, let us say this portion, it could have been put on top of this also, right. So, one can put this like that. Okay, whatever I am showing here, it would have been flipped and put the other side. When you do that, it does not compensate this one. Okay. It has to be put downwards, and the way the rotation happens and what it moves, it is going to compensate. It will have much less motion in the vertical direction. The folded flexure mechanism feature is that. People came up with very clever configurations. Here is another one where the stage does not move because of symmetry. So, now if you look at this central one, because of symmetry, it will only move in the, if I call that x direction or q1 direction. It will not move in this direction at all. Okay. So, it is a symmetric, here what is used is symmetry. By using symmetry here, we are able to get a stage that has only one degree of freedom, one translation. The other translation, the vertical direction is removed, and there is rotation also that is absent here. So, only this motion is possible for this mechanism. So, that is how we can use these 8, actually there are more, 16 now, right. These are all the elastic pairs, 8 on either side, total 16 elastic pairs are used to get a precision stage. And here is another one which is also the folded flexure, but there is also a lever. Again, look at the portion, let me use a color that you can see. This is the extra portion now. Okay. The 1 to 7 are already there in the previous one. Now, we have 8, 9 and 10, these segments are there. Now, you can see the lower stage and upper stage are coupled through a lever. Okay. So, this is the lever, there is a pivot here, this is there is a here and a B. You can adjust this A and B. So, let me change the color of the ink. There is A here and a B here. This is length B is this, length A is this. By adjusting this A and B, and of course, there is some distance that you can have here also. By adjusting these lengths, you can couple them so that this stage and that stage you can do further compensation. Previously, I said that by having this folded flexure, you can reduce the vertical motion of that thing, so that it moves mostly that way, very little this way. By coupling it further, you can reduce it even further. So, people use this to get stages that have the motion in the way that you want, mostly in one axis or two axis. And sometimes you can do even more complicated motion with this just flexures. One of the ways that you can do is to start with a rigid body mechanism, which is over here. So, everything you can see the joints, there are joints here, there is one more joint, 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 joint and joint. In fact, these are all good examples for trying your mobility formulas, Grubler's formula and then Maxwell's rule, which are equivalent when there are only bars and joints, not other pairs. Okay. So, these are all good examples to see what is the mobility of this. This particular rigid body, this is rigid body mechanism, which has rigid bodies and kinematic joints. This is rigid body mechanism, whereas this one here, which is exact equivalent of that. If you notice, wherever these joints are, we have these flexures. So, let me put a flexure corresponding to that. Okay. And likewise, if I want to see where this flexure is, we can see that that is also over here, right. So, everywhere that we have these flexures coming, and the actuation here that is the force over there. Okay. So, this is a compliant mechanism, with elastic pairs. If you look at this, one would think that it is very easy to design compliant mechanisms, which it is. You take a rigid body mechanism and replace all the joints with elastic pairs, and you get a compliant mechanism. And these are, although they look very simple, they are used in very sophisticated instruments and precision instruments applications. This is actually an X-ray interferometer, where there is precise motion that is required for something called this analyzer, okay, where X-ray is split, the beam splitter, and there is a mirror. They have to be moved ever so little, not all of them. This analyzer is what is moved. When you move that, these X-rays, actually the movement of this has to be of the order of angstroms. That can be done with these mechanisms. This is made of, as you can see, single crystal silicon monolith, very small, and the motion of these are going to be very, very small. By achieving such small motions, you can create very sophisticated instruments, even though mechanism, from the mechanism viewpoint, they look very simple, but they have very important applications. Here is another one which is for friction measurement. So, again you can see our familiar parallel motion flexure there with 4 elastic pairs. Okay. There are a lot of applications of these in precision machines. Here is another precision flexure mechanism, again you can see the joints. Okay. And you also see slightly different type of flexures now. These are circular corner flexures, as they are called, or circular notch flexures, whereas these are little longer. They are called small length rotational elastic pair or small length flexure. What is important for them is basically this segment that can bend, as it is shown here. It was straight to begin with, like this. Let us say this is the base, okay, and there is a relatively rigid body over here. If there were to be a movement acting on it, this is going to deflect. This is going to deflect like this. Accordingly, this rigid body portion is going to rotate. They are small length because this length is small compared to the size of the rigid bodies. Okay. They are also used widely in precision motion stages. You can see, if you look closely here, you can see these small length flexures over there, over here, over there, over there, and over here and there. The symmetric arrangement. You take a parallel manipulator and replace all the joints with flexures, you get precision motion stages, and these are used widely, as I already said, and they are very expensive also. All microscopes and all microscope AFMs and everything that needs scanning need stages that move very precisely. People use these flexures. This technology has been around for a very long time. And there are different forms of flexures. We saw the circular notch one and small length flexure. There are also what are called cross strip flexures. Now, here you see there are 4 strips. So, this is 1, 2, 3 and 4, which are arranged in a cross fashion, and here also there are 4 flexures, but they are attached at the center. Okay. Here maybe some assembly is required to bolt these things between base and the stage. This is the base and this is the stage. Okay. So, this is the base. So, you can connect them, but here it is monolithic. So, there are a lot of different types of flexures possible. Here is another one called cruciform flexure. So, what you have here is the cross section of a beam or a small flexure is plus. It could be a cross also, or just a plus or a cruciform as it is called. So, this is very interesting because it actually twists. It's a torque is applied over here, for if you think of this as a short beam, it is a short beam. You have to, when apply, this is again the base and this is the stage. Here the stage rotates, but cannot bend as easily, because the plus cross section will have very high second moment of area either direction. So, the bending about let us say this way or that way is going to be very difficult. The stiffness is very high, whereas rotational or torque stiffness here is low. Okay. Here is a manifestation of that, so that it is able to rotate about this axis more easily, but cannot bend, right. And you can put two of those, so that it rotates about that axis, rotates about this axis. You have a universal joint, compliant universal joint. What we have here is a compliant universal joint, because it allows two rotations between the base, which is the base here, and this I can call it stage or whatever rigid body that you have, that will have two rotations related to the base. And you can also have them in 3-dimensional fashion. Here there is something shown. You can take a solid cylinder, cut out with, let us say, wire EDM or water jet cutting, where you can make sections the way it is shown there. I have a little piece here that you can see. It may be difficult to see, but maybe we will have a little focusing happening. What I have shown there is a very little piece, a cylinder that can tilt like this, okay, that can also tilt like this. That is what I meant a universal joint. So, if I attach a body here related to the base, this little cylinder with those couple of cuts can tilt like this and tilt like this. This has an interesting feature that you cannot tilt more than certain angle, because if you come back to the slide, we can see that when it tilts, this is going to just touch. So, over here when it tilts, it is going to touch the other surface, it cannot move much. There is limited motion, but it is going to be strong because it is not going to be excessively deformed. With such a thing, if you take a long cylindrical rod, by putting these cuts, this is a different design what you saw here, but the easiest thing is to cut halfway through like this and then turn around halfway through there. If you keep on cutting like this, a steel rod can be bent like an elephant's trunk, or for that matter anything. If you have granite pillar, if you cut like this, that can also be bent, okay. But limited motion, you have to limit motion like that is shown in this particular design. And you might also have seen these toys. So, what you can do with elastic flexures. So, here is a little toy with wooden, where this tail, like what I meant, that if you take a cylindrical rod and put this thing, you can do that. It has actually that. So, this crocodile toy that you find in the markets, that is, it is all with flexures. So, with flexures you can get any amount of displacement, but at each elastic pair the motion is limited. And 3D flexures, if you look at the slides again, you can have two circular notch flexures with axis rotated, or you can have a 3-dimensional equivalent of this circular nut hinges, with which you can make a stage like this in 3 dimensions. So, you can see now these things are 3-dimensional versions of circular notch hinges. Now, you are removing orbs of sphere from the a cylinder to create this. Okay. So, there are lots of things they can do with flexures. In the next part of the lecture, we will look at the details of what this stiffness is and how we can model these flexures.